Thank you, everyone who is joining us. We have a few announcements as you all hop on. First, we're recording this session. It will be available in Whova, our conference app, within 2 weeks after the Congress ends. And we kindly ask that you keep your microphones and cameras off during the presentations and follow the presenter's lead on when to engage with them. If you'd like to ask our speakers a question during this session, please use the Q&A area to the right of your screen. The chat window is there where you can engage with other attendees as well. Looks like we're ready to get started, so I'm going to hand it over to our speakers to begin.
Good afternoon. I am Theresa Jain, and I will be your moderator today. So this session, this special session, is going to really kind of give you an update of what we know about landscape fuel treatment effectiveness. Change the slide here. Next slide. So in 2019, the Joint Fire Scientists contacted me to see if I could put a science team together to conduct a literature synthesis with a focus on treatments across the landscape. How are they basically mitigating adverse wildfire effects? How are they providing opportunities for wildfire management? Are field treatment planning integrating both past and future wildfires? And the objective of that was to really determine if the literature, the current literature, can inform future fuel treatment planning and identify management and policy relevant research gaps. Next slide. So I put a team of scientists together from throughout the country that have expertise in basically every ecosystem that burns in the United States, from grasslands all the way to forests. And it's quite the adventurous team. And together we put together a strategy and an approach to address the questions that Joint Fire Scientists wanted. Next slide. And so what we're going to do is we are going to basically do 5 talks, beginning with Sharon Hood, and really tell you what we learned from the literature synthesis. So Sharon, why don't you begin and start talking with the foundational concepts of what we mean by fuel treatment effectiveness across landscapes.
Okay, thanks, Terry, and thanks everyone for joining today. As Terry said, this talk here is really an outgrowth from the JFSP project, and the main objectives where we decided to step back and see if we could develop a framework for quantifying fuel treatment effectiveness from stands to landscapes. So when I talk about fuel treatments, it's really the manipulation or removal of fuels in order to change the fire behavior. So we're thinking about ways to reduce the likelihood of ignition or fire spread, some sort of ways to make it easier to control the fire, put it out, and to lessen the potential resource damage. And we focus on fuels because, going back to the main components of the fire behavior triangle, it's fuels, weather, and topography. Fuels are really the only thing we can change. So we develop fuel treatment prescriptions in the context of that local topography and anticipated weather patterns to basically, if a fire does occur, that we have fire behavior that would achieve our desired effects. So fuel treatments is a very large umbrella term, and there's some main objectives. Again, the reducing and rearranging surface fuels is a primary objective of virtually every fuel treatment. When talking about forest fuel treatments, there's also these guiding principles generally of trying to increase the crown base height, that the remove fuel between the ground and the bottom of tree crowns, are to increase canopy base height, and then to increase spacing between tree crowns or reduce canopy bulk density to make it harder for a fire to spread from tree crown to tree crown. And we also have the goal of retaining larger trees of fire-resistant species, so that when fires do occur, again, we have the fire behavior such that many of those overstory residual trees can survive. And so there's a lot of challenges to our fuel management programs, especially our large national programs like in the United States. This is just a map here of wildfire hazard potential that was developed by Greg Dillon and others. And this is showing areas where if a fire occurs, it's highly likely that it would be difficult to suppress those fires. And we have over 200 million acres alone in the United States in high and very high wildfire hazard. So it's a big challenge to scale from our project level and stand level treatment prescriptions up to landscapes to really think about how we might be modifying fire behavior over large spatial scales. Another big challenge is how to incorporate time. And this is both from the time frame of how long a fuel treatment is effective for, as that vegetation starts to regrow after any treatment is implemented, and also thinking about time as far as just the annual variation in climate and extreme weather from fire season to fire season, that we that the time isn't right now isn't very well incorporated into thinking about fuel treatment effectiveness. We also have a big challenge about how to incorporate individual fires or individual treatments into the big picture. To see, it's easy to cherry pick individual fires or treatments and say this worked, this didn't, but we don't have good metrics right now to say what percentages are working or what are and why that things might be working or might not be. And that's because we have a lack of way to tie our have quantifiable measures that are related to objectives. Again, at these coarser scales of the regional or national level. Like all projects have identified objectives, but these can often get lost when we start to scale up. So our current measures at landscape and national scales, again, are very coarse because, again, they need to be, but I would argue that they might be too coarse to really start to move forward our discussion about how we start to live with fire and what sort of fire effects are occurring. Right now with our field treatments programs, we report in the United States just acres treated by activity type or an area in very high wildfire hazard potential. So these are just basic numbers. They're not tied to actually what those prescriptions are and how if they're treated in a way that might actually modify our fire behavior. At the end of every fire season, we also report in the United States the just number of fires and acres burned. And I would argue that these numbers are virtually meaningless, that because most of those fires might be less than an acre in size, or they might be 500,000 acres in size. And that just reporting numbers doesn't tie into what type of fires are and the distribution of those fire sizes. Same with acres burned. Both of these metrics imply that kind of all fires have negative consequences. And we know that's not true. So it really doesn't help us to move forward any discussion about the potential benefits of fire when we report things so coarsely. So how do we start to shift from reporting acres burned to how did the fires burn? What sort of effects are we seeing from fires? Well, we are proposing this this framework about ways we could start to quantify effectiveness of fuel treatments at larger scales. And the first step of this that we envision is starting to build a table, and that this could really work as a communication tool between interdisciplinary teams or collaboratives across different management scales, from local to regional to national scales, where we start to identify important attributes of interest, both at the stand scale and landscape scale. First with looking at hazard state, so identifying the actual state of fuels over a landscape and what the potential fire behavior is at that. So many of these attributes are already developed. And then the second part of that evaluation of hazard is also the evaluation of our risk state. So defining these risk states through selected attributes. And that's the risk here is looking at the actual likelihood of ignition under a given fire intensity and what we expect that loss to be, or response function to be. Then moving to phase 2 with this evaluation is the evaluation of the actual fuel treatment effectiveness through environmental attributes and social attributes. And these are actual outcomes of fires. And so I'm going to step through this in more detail in the next slides, but our hazard states are primarily data derived, so either field based or remotely sensed data products that are of the actual state of fuels and in a given area at the moment, at any one point in time. Then there's also modeled output for hazard state and risk state based on many of our fire behavior and fire effects models. And I put those down as subjective because they are based on any of the assumptions embedded in models, and also any of the choice that modelers use for inputs. And then what's really different here with phase 2 is that the evaluation of the fuel treatment effectiveness, those are all actual data derived and objective attributes. So we're not using modeling here, but really thinking about what are the true outcomes of these fires. It's not just acres burned or number of fires. And I put these arrows over here just to show that this has to be done annually at a minimum to see how things are changing over time. So these are just some of the example attributes that we thought could be of interest about having to describe the state of different fuels and potential fire behavior. And many of these are already available. And at the risk state, this is where we get into the likelihood of ignition based on actually where you are, given your weather and topography, and the exposure and susceptibility. So different attributes for the fuel treatment effectiveness are these actual fire effects, both from environmental and social attributes. So once that table is completed, the next step is how to actually visualize all the data. And so there's a lot of really awesome products right now. I just put up 2 that have a lot of traction in the United States with the pods and fire sheds, where people are using these tools to quantify risk and hazard and fuel suppression responses, or fire suppression responses in the US. But what's lacking is really how to either further condense the data behind these maps to show something simply, but not just as simple as one number, because one number, like a mean or an average, does not give us enough variation. And so we think that using box plots to show data distributions is a really effective but simple way for people to start to think about how to couch individual stands or fires in the context of a whole pattern of fires on a landscape or treatments on a landscape, to where you can see your median values, but you can also see kind of your upper and lower bounds. And so how we visualize this working, or imagine this working, again, is moving from these basic reporting metrics of number of fires and acres burned to something that shows a much bigger picture, because fires are being, and our landscapes are being managed for so many different types of resources. So this is how we think this could work, is that groups could come together and basically identify your target or desired values. And so knowing that our landscapes are very complex and being managed for different things, there's not going to be one size fits all prescription for every acre of land. So really thinking about what is our acceptable range of values for any one vegetation attribute within a given ecosystem type. And what we would like, this is kind of these green boxes are what we would like the landscape to look like. And then we can also using many of the products that are already available, we can plot our actual current values of those attributes. And this allows us to start to have conversations about seeing, one, how far are we away from our where we want to be, and how do we start to get there? So this is it can be done before fires. Again, it will be done annually to see as treatments are implemented and fires occur. And then also you would do this, evaluate this post fire to again show effects, so that you can imagine over time, you would hope that these black boxes would begin to start moving toward our desired target areas identified by the green boxes. And so this test, we hope, we're still fleshing these ideas out, but we hope that it can allow more communication and also just a more nuanced view of the complexity of wildfire management and field treatment programs in over large scales, to show how these how fires and field treatments are changing fire behavior at the landscape scale. So we think that this framework could be a relatively simple way to quickly envision or to see current fuel hazard and risk, as well as the fire effects that relates directly to objectives over time. So with that, I might have some time for questions, and thank you for listening.
Thank you, Sharon. I do not see any questions at this time in the Q&A area, but we have about 2 more minutes. So if anybody would like to add a question, we can definitely do that. During that period, Sharon, do you have any examples of that concept? Have you seen any specific examples about how you guys propose to do this on the ground?
Yeah, we haven't made it to that step right now. We've just we've started kind of this process, but I think the next step is to definitely identify an area and try to implement this as a proof of concept.
Okay, thank you. Well, our next speaker will be starting in 1 minute. In our synthesis, we kind of broke our synthesis into 3 areas. One of them is looking at empirical studies. And Shawn McKinney will be leading the presentation on what kind of empirical information we found in literature synthesis, and then present some of those results. So Shawn, you have about a half a minute to get yourself prepared for that. So
I'll go ahead and show your video, Shawn. 1 second, everyone. We're just gonna have a video to share. Alrighty, it should be showing up shortly.
attending this presentation. I'm Shawn McKinney, and I will be presenting results on our search for empirical evidence of landscape.
Sounds like y'all can't hear the video, but let me just do a little troubleshooting and we'll get it going. One of those tech days. All right, let's try to screen share this again.
Site level effects. It is not possible nor desirable to treat all locations across broad spatial extents.
Can y'all hear it now?
Hello, everyone. Thank you for attending
Restarted
this
it.
presentation. I'm Shawn McKinney, and I will be presenting results on our search for empirical evidence of landscape level field treatment effectiveness. I'd like to acknowledge my co-authors, Alana, Terry, and Nate, as well as our funding sources, the Joint Fire Science Program and the U.S. Forest Service. Field treatments can generally be characterized as the manipulation or removal of vegetation to create conditions that mitigate wildfire impacts. In forested ecosystems, ideal characteristics are high canopy base heights, separated tree crowns, reduced and discontinuous surface fuels, fire-resistant and resilient species composition. There are a diversity of approaches to field treatments, including a variety of mechanical methods, prescribed fire, and wildland fire. There is ample empirical evidence that field treatments can mitigate wildfire effects within the boundaries of the treated areas, what are known as site-level effects. It is not possible nor desirable, however, to treat all locations across broad spatial extents. There is therefore a need to implement treatments in a manner where their effect is realized in areas outside of treatment boundaries. From simulation studies, we know that treatment type, spatial arrangement, and their relative density can alter wildfire behavior in untreated areas, that is, outside of treatment boundaries. These are known as landscape level effects. The landscape level effect hypothesis states that field treatments can have mitigating effects on wildfires in areas outside of treatment boundaries. If this hypothesis is true, then there will be a spatial pattern of fire effects influenced by treatment design. For example, their location, their relative density, and their type. To test this prediction, a study must quantify a link between conditions within field treatments and some metric of fire behavior or effect outside of the footprint. In this conceptual diagram, in both A and B, the dark outer line represents the perimeter of a hypothetical wildfire, and the dark circles within it represent treatment locations. In scenario A, the lighter lines represent contours of influence, where the effect of the treatment permeates into untreated areas and decays with distance from treatment boundary. Asymmetric contour shapes reflect the notion that fire behavior outside of treatment boundaries will also be influenced by spatial heterogeneity and biological and physiographic characteristics. White areas represent untreated areas in both A and B that are unaffected by conditions within the treatments. In scenario A, it can be interpreted as a prediction of the landscape level effect hypothesis, that if true, there will be a spatial relationship between within treatment and outside of treatment conditions during a wildfire. Scenario B would not provide the necessary information to test the landscape level effect hypothesis, and is instead considered site level. That is, inference of treatment effect is restricted to within treatment boundaries. The text in the right-hand column of both A and B just gives some scenarios that we could test this hypothesis on. You would find out the same information for within treatments. How did fire severity change, for example? But with outside treatment effects, we could only see that in the landscape level. And we might want to know, how does severity change as a distance from treatment edge? Was there change in spread rate? Was there change in extent? We would not be able to determine this from a site level approach. We addressed two research questions for this study. First, is there empirical evidence supporting the landscape level effect hypothesis in the literature? And if there is there enough detailed information to inform strategic and operational decisions, such as spatial and temporal deployment, density, and combination of treatments? To address these questions, we conducted a systematic literature review, whose approach can broadly be described as search, select, extract, and synthesis and analysis. In this particular study, for the empirical evidence, we extracted 39 different variables from each of the papers we identified. We grouped these papers based on similarities and described them based on the 39 variables. We did some correlation and some graphical analyses. The empirical study is one aspect of a broader investigation into landscape level fuel treatment effectiveness. That is the basis of this special session. This diagram depicts the literature search and selection processes leading to the separation of the three sub-studies. Personnel from the Forest Service Library conducted the literature search in 2019 using multiple databases and numerous keywords. We wanted to take a broad approach so that the likelihood of missing a key paper was minimized. Thus, the initial search resulted in over 2,000 papers. In phase 2, we reviewed the papers to determine if they met our inclusion criteria, mainly that the terms field treatment and landscape were used in a manner appropriate for our study. That landscape was an area larger than the treated area and with a potential to be influenced by the treated area. We also set a rough study area size guideline of about 35 square kilometers with no minimum treatment size established. For the empirical study, this resulted in 26 papers for review. Here we see the distribution of study sites among the 26 studies by level 3 ecoregions. We see the Western US forms the vast majority of study sites. Within Western sites, ponderosa pine and Douglas fir were the two most common species studied, occurring in 74% and 52% of sites respectively. We extracted information on wildfire size and total treatment area within wildfires to help describe the empirical studies. There were 93 pairs of wildfire and total treatment areas. Both x-axes are in hectares and have been log 10 transformed to account for skewness introduced by the few very large values. Average wildfire size was around 9,500 hectares, and average treatment size was close to 2,000 hectares. The correlation between wildfire size and total treatment size was surprisingly strong. Again, on the x-axis, we have wildfire size in hectares, log 10 transformed. And on the y-axis, the treatment sizes within each wildfire. So those are total treatments, not individuals, and how they paired together. Correlation was 0.89, and the average percentage of a wildfire that had been treated prior to the wildfire was 22. Additional pertinent information we extracted from each study were treatment methods, how they described field treatment effectiveness, how they described a landscape scale of field treatment effectiveness, and what the response variables were. In this graph of treatment methods, we see that prescribed fire only represented the most frequent treatment method, followed next by thinning only, wildland fire only, and thin and burn. Those four methods represented about 65% of all of the observations. But you can see other methods within the literature. Field treatment effectiveness was generally characterized as changing a particular factor in a desirable direction. All studies characterized it a similar way. We identified 11 factors of effectiveness, with severity, behavior, and spread being the most frequent, representing 58% of all factors. When we tried to tease out what authors meant by landscape scale field treatment effectiveness, we found that only one study attempted to define what they meant by landscape. In this case, there were about 13 factors that generally tried to represent this broader context, but they were similar to the overall field treatment effectiveness. And here, severity, spread, and forest structure were the most prominent, representing 65% of all factors. Response variables were a broad variety, but they included the typical fire-related variables, as well as many other ecological variables. And data for response variables were collected in both the field and from remotely sensed imagery. All 26 studies met their objectives of altering wildfire outcome in a desirable direction. And all 26 studies documented site level effects. That is, changes within treatment boundaries compared to outside of treatment boundaries. Only 11 of the 26 papers documented landscape level effects. A 12th did address it, but failed to show an effect. 3 parameters were identified at this landscape level: severity, extent, and progression. No single study exclusively addressed the landscape level. Here we'll focus on the subset of studies that demonstrated landscape level effects. Severity had the most evidence for it. There were 5 different studies that showed a positive effect of field treatments on wildfire behavior, wildfire effects outside of the treatment footprint. There was a negative relationship between the proportion of the landscape treated and the proportion burned at high severity, looking at 3 spatial extents. There is a lower proportion of high severity in a splat, which is a strategically placed landscape area treatments, compared to an adjacent untreated landscape. There is lower proportion of high severity in areas adjacent to large prescribed burns compared to untreated areas farther away from them. A large area of low severity was observed in an area with a high density of field treatments. Fire severity increased with increasing distance from prescribed fire patches, with the effects terminating 200 meters from the treatment edge. The second parameter that we have evidence for a landscape level effect is wildfire extent. In 2 related studies that used wildfire data with simulation, they showed that there was a decrease in wildfire extent that was strongly correlated with the proportion of area treated. However, this decrease didn't occur in all cases. In 11 of the 14 fires, treatments reduced the extent by about 13%. However, extent increased in the other 3 fires. In a similar study, looking at 54 wildfires, extent decreased by 64% with fuel treatments applied. However, in 19 wildfires, extent increased by 34% with fuel treatments applied. For fire progression, there are 2 main ways of looking at it: fuel breaks conducted by management and previous wildfires that could act as fuel breaks. In 23% of wildfires intersected a portion of a fuel break in a study in Southern California National Forests. A range of 22% to 47% of the fires were stopped, while 29% to 65% of them crossed the break. In these cases, suppression was critical. Less than 1% of the fires stopped by break alone. So the fuel breaks, as they were intended, acted as an element to help suppression activities. In a similar study, also in Southern California, 43% of fuel break intersections constrained the fire, while 57% spread across the break. Similarly, only 1 fire was altered without suppression. Looking at previous wildfires as potential fuel breaks, 60% of over 1,000 wildfires intersected the boundary of a previous wildfire, demonstrating that there's ample opportunity of wildfires to act as fuel breaks. Progression of the fire was limited by previous wildfires, but this effect decayed with time and with the warmer and drier conditions of a forest. such that cooler and wetter forests had longer decay times. In another study, 40% of wildfires encountered the perimeter of a previous wildfire, and fire progression was limited 8.7 of these. Similarly, the effects decayed with time since fire. Circling back to our research questions, is there empirical evidence supporting the landscape level effect hypothesis? The answer is yes, there is. Secondly, is there enough detailed information to inform strategic and operational decisions, such as the spatial and temporal deployment, density, and combinations of treatments? The answer currently is no, and this is an unsurprising result. Although the number of opportunities to perform natural experiments increases annually with each new wildfire, the requirements of implementing a robust sampling design needed to obtain the necessary empirical evidence are immense. The empirical evidence of fuel treatment effectiveness at a landscape level generally supports results and subsequent predictions from simulation studies. That is, wildfire behavior can be altered outside of a treatment footprint. However, stronger predictions, such as the specific spatial configuration and size that is optimally effective, remain untested. Fire severity, extent, and progression were all shown to be mitigated outside of treatment footprints, laying the foundation for more detailed investigation on how to optimize spatial and temporal implementation. One other important finding we think is worth highlighting is the distinction between landscape as a process and landscape as a scale. Wildfire is a landscape level process. Fuel treatment effectiveness should be evaluated by how it affects that process functionally from a landscape perspective. For example, notions of patch dynamics, contagion, proximity indices. Landscape scale or landscape size, as they are often used, have little generalizable meaning. Large wildfires and/or large treatments may be called landscape, but inference will still be constrained to within site if site level is the design and the analysis. Therefore, landscape level designs need to be implemented to understand landscape level effectiveness. Thank you for listening to my talk, and I will take any questions you now have.
Thank you, Shawn. Right now, I don't have any questions right now, but I think one of the things that pops into my mind, Shawn, listening to Sharon's discussion, did you get any ideas how we could have shown how we could pursue an empirical study, kind of taking that idea that Sharon did provide on those measures?
Yeah, I think the table is a good idea that Sharon proposed. Getting the necessary data to fill it will be, challenging. So I think there's plenty of opportunities, obviously, with every fire. I think the main point from our study coming back is thinking about it ahead of time a little bit more about this concept of a broader spatial extent of affecting your treatments having effect outside of their boundary. Looking at transects from the center of a treatment out into the burn is a pretty straightforward one. And I think there's just a lot of different levels to this. To get it to an operational level where we say this is going to be the most effective, I think will be really difficult. To continue to show that there is an effect will be less difficult. And that's just kind of really collecting the appropriate data.
Thank you, Shawn. Okay, our next speaker is going to be Jeff Ott, and his focus is going to be on the model simulation portion of the fuel synthesis. And we have about a half a minute, Jeff, so don't quite start for a little while, but you can upload your slideshow.
All right, I'll go ahead and get started here. My talk follows up on the previous two. In this case, I'm looking at a set of studies that use simulation approaches to address this topic of landscape scale fuel reduction treatment effectiveness. Shawn alluded to this. Simulation is one approach we can take, which is simpler than carrying out experiments or waiting for fires to happen in the real world. So a lot of studies have been done, and there's some useful information that comes from it. I want to start off by recognizing my co-authors, Francis Kilkenny and Theresa Jain. Special thanks to individuals and organizations and others, the fire research community that contribute all these studies I'm going to be addressing here. My presentation is stuck. So the conceptual basis for this topic is that if you modify fuels on a portion of a landscape using some type of fuel reduction treatment, these treatments can affect fire spread and fire behavior not only within the treated zone, but also the surrounding landscape. And it's possible to measure this effect using fire simulation modeling. And these diagrams illustrate a method of fire simulation developed by Mark Finney. On the left, you can see various ways of depicting fire spread and the fact that these patches with lower fuels are acting as a barrier to that spread. And this is just a simple model, but it can be applied to more complex situations in real landscapes. So over here on the right is some landscape representations. The red lines are areas of high fire influence where fire would be expected to spread. And these purple shapes are then fuel treatments that are simulated that are placed on the landscape. And the idea is that these will disrupt those paths of fire spread. What they found in this case was that by placing these treatments on 15% of the landscape, the amount of time it took for the fire to spread from one side of this area to the other was cut by half. So this is useful because as the other speakers have mentioned, it's not feasible to think about treating all areas everywhere. So the question of how to maximize the effectiveness of a limited set of fuel treatments is important. So for this set of the synthesis, there were certain criteria that we used. We followed that process that Shawn described of going through the literature, looking for studies that met this criteria. The ones that were selected included a comparison of landscape scale scenarios in a simulation framework, where one or more of these scenarios was a fuel treatment reduction. There was simulation modeling that was used to measure fire response, and these were all landscapes from the United States or Canada, either actual landscapes or simplified landscapes in some cases that were based on conditions from these countries. And I'm showing an example from some work by Kevin Osborne. This is a landscape in the Klamath region of California. You can see the outlines of this landscape and the different scenarios. A no treatment, and then different types of fuel treatments that were applied. The no treatment scenario is useful as being a point of comparison, like the equivalent of an untreated control in an experiment. I'm going to be using that language, but keep in mind when I talk about the experimental treatments in this case are the scenarios themselves, which is different from the fuel treatments which are embedded within the scenarios, as you can see here. Each of the treatments, each of the studies used this process to evaluate fuel treatment effectiveness. So each of the scenarios was subjected to fire simulation modeling, and then there was some metric of fire response, such as burn probability or wildfire area, that was measured. A comparison was made among these scenarios. And you can see here from these bars, no treatment had the highest fire size. Other of these treated scenarios had lower fire size, and you can gauge the amount of effectiveness based on some measure such as this. This was the type of information that we extracted from these studies wherever it was available. So here's a rundown of the studies that were included. There were 85 papers that met the selection criteria. Most of them were journal articles. There were also some government publications, proceedings and book chapters, theses and dissertations. A total of 94 studies, where a study is a specific landscape that was examined in a paper. Some papers looked at multiple landscapes. You can see the location of those landscapes here on this map. Most of them were in montane areas of the Western US. The landscape size ranged from just over 200 hectares to over 3 million hectares, broad range. Some of these studies were just based on a single year simulation. 39 studies just looked at conditions for a single year, whereas 55 studies followed the simulation over multiple years, up to 250 years in one case. There were a variety of different modeling techniques or platforms that showed up. These are techniques that either just model fire specifically or include fire within a broader landscape simulation context. And so some of the common ones included Farsight, FlamMap, FFVFVS, Landis. Some of them build on each other. There's been this progression of development of different techniques over the past 30 years or so. Some of the studies also use treatment optimization techniques. These are algorithms that will help to determine where you might want to place your treatments in a way that optimizes some desired outcome. The most common of these in these studies was the treatment optimization model, or TOM. So we follow this data extraction and summarization procedure to get data that we then put together in what I'm calling a summarization. It's not a true meta-analysis, but it is summarizing data quantitatively at a meta level across studies. In this case, we focused on response variables directly related to wildfire, such as burn probability, burn area, and so on. Each of these variables is going to be higher when there's more fire. But we're also interested in looking at the type of fire. So wherever that was defined, we separated all wildfire from damaging wildfire, which was fire that was high intensity, high severity, or had some other label to indicate that it was damaging. And on the other hand, beneficial wildfires were those that were low intensity or low severity. So we extracted mean values of response variables for each scenario. And we use WebPlot Digitizer to extract values from figures where necessary. If there was more than one representative response variable, we used one representative response variable if there was more than one available. And then we summarize values for treatment scenarios relative to untreated controls. This was a step to standardize across the different measurements and units and focus on the effects of treatment relative to the scenario where you're not treating. So I'm going to show some figures here that kind of summarize across studies what we found. Here we're looking at treatment effectiveness just for a subset of the studies that represent California landscapes. Each of these lines here is a different study. You can see the landscape and the citation. Each of the dots is a scenario that was tested in a given study, and these are color-coded by the response variable. And in cases where there were multiple years, this is just showing the mean across those years. So this is just a simplification of the data. You can see these panels for all wildfire, damaging wildfire, and beneficial wildfire. And the x-axis here is fire response relative to the untreated scenario. Anything to the left of the red line, it was less than the untreated scenario. Anything to the right, it was more. And the the main pattern for all wildfire and damaging wildfire, most of these scenarios were less. For damaging wildfire, that's what you would want. For beneficial wildfire, there weren't as many cases where that was measured. These tended to be higher than the untreated, which again is what you would want for that. So I'm expanding now just to show quickly across all of the studies that had this type of data available. This is the part that I just showed for California, but now you can see the same thing for Oregon, Washington below, and then on the right side, all of the other states and provinces. And basically the same pattern that I was showing for California is repeated in these other cases, but there are some outliers and exceptions, instances where treatments were not effective. And so it wasn't perfect. Just to summarize how that panned out, tallying up these for these different categories. All wildfire, 86% was lower than the control, 14% was higher. For damaging wildfire, 94%, so pretty good in terms of effectiveness. For beneficial wildfire, where higher than control is what you want, 79% were there. So now I'm going to move beyond this basic question of whether or not field treatments were effective. And now looking at the question of what made some treatment scenarios more effective than others. And so to answer this, we can look at the factors that were tested in these studies. And I've divided these into two categories. There are those factors that were part of the field treatment design and deployment. Extent, the total area treated, the size of individual treatment units, the placement or spatial location, arrangement of treatments, the timing of treatment implementation, and the prescription or technique used for fuel reduction. Each of these studies looked at least one of these factors, and many of the studies also looked at factors beyond the treatments, such as fire weather, climate scenario, other things dealing with fire and fuels, suppression effort or ignition management effort, these sorts of things. Some of the most informative studies were those that tested multiple factors in what was the equivalent of a factorial design. So they're looking at how these things relate to each other. And this allowed the studies to identify interactions between different factors and which ones tended to be most important in determining fire effects on the landscapes. So rather than going through all the results in detail for these different factors, I'm just going to point out some key findings. And then if there are any specific questions, we can go into more detail. We found that the study showed that treatment effectiveness was generally greater with larger treated area, sometimes but not always with diminishing returns as treatment area increased. So what this means is that for some studies, once you reach a certain treated area, usually around 30%, additional treated area had less of an effect. But that wasn't the case for all of the studies. There were some that continued to have an effect as treatment area increased. Using optimization algorithms to determine placement and or timing of treatment led to greater treatment effectiveness compared to other schemes. So the studies basically showed that these algorithms were effective for their intended purpose. Prioritizing treatments in stands with greatest fire hazard or risk generally led to greater reduction of damaging wildfire at the landscape scale compared to prioritizing stands near the wildland-urban interface, but the latter was generally more effective for protecting that interface. So what to prioritize can depend on what's most important to protect in a given setting. Prescriptions that focus on outcomes other than fuels reduction, such as commercial harvest or habitat restoration, were often less effective at reducing fire impacts. And many of those cases in that figure I showed where the treatments weren't effective were cases where the primary objective of those treatments was not actually fuels reduction. More extreme fire weather led to greater wildfire extent, but not necessarily less treatment effectiveness relative to untreated scenarios. So this is partly because as the amount of fire increases, there's a greater probability that those fires will intersect with the treatments and thus play a role in affecting fire at the landscape scale. Effectiveness varied across climate change scenarios due to effects of climate on both fire weather and vegetation fuel dynamics. So there were some surprising results in some of these studies in terms of what you got when you looked different climate change scenarios, because climate affects both the fire weather and the buildup of vegetation and fuel. There were relatively few studies that actually looked at climate change. So this is, I think, an area where future work is needed, and studies that carry out simulation modeling using conditions that are expected to occur in the future is going to be increasingly important, obviously. So that concludes what I have, and I'll open it up for questions.
Yes, thank you, Jeff. I have a question from Matt Thompson. Did any of the studies look at options for expanding beneficial fire at the landscape scale, or just characterize beneficial local effects as a function of localized intensity?
Yeah, as I showed on those figures, there weren't a lot of studies that focused on beneficial effects. The measurements I presented were all at the landscape scale. So it included what was happening in those treated areas and beyond. But yeah, I think there's potential for more of that, looking at the beneficial effects.
Thank you. There was a question that Matt also provided, and I'm just going to read it off. Federal agencies in the U.S. are about to receive billions of dollars to implement landscape fuel treatments. If there isn't an evidence of optimization treatments, how would you suggest we move forward? And this is actually a question for Jeff and Shawn as both, and we only have about 2 minutes. So Jeff, can you do a half-a-minute answer to that? So
the question is related to optimization. Just repeat that part about the optimization. So
okay. Okay, if there isn't sufficient evidence to optimize treatments, how would we suggest we move forward? Okay, on the modeling, we have optimization, but how do we move it to the empirical part of the research? And then how do we move it to the ground?
Obviously, with simulation, it's easy to implement, and you don't have to deal with some of the realities of feasibility and other restrictions that might prevent treating certain areas. The optimization algorithms, as I was mentioning, are useful. And I think building on those, finding ways to optimize to the extent possible under the constraints that are out there, I think is one way to move forward.
Okay, thank you, Jeff. We don't have any more time for any more questions, but we're going to move on to our next presentation, which is provided by Brice Hanberry, who is also a researcher for the Rocky Mountain Research Station. And she's going to be focusing her presentation on the manager input via the case studies that we have that are documented case studies.
I'll go ahead and start playing shortly. 1 minute, please.
Thank you for zooming by to listen to this presentation, which is one of a symposium about landscape field treatments, a project that was funded by the Joint Fire Science Program. In this presentation, we are focusing on manager eyewitness accounts that documented fires and effects of treatments at landscape scales. The photos from the case studies are quite fantastic, so you may want to follow up by viewing some of the reports. My name is Brice Hanberry, and I collaborated with Ali Urza and Theresa Jain, and we work for the Rocky Mountain Research Station of the USDA Forest Service. Frequent surface fire was the historical disturbance regime throughout most of the United States, and this understory disturbance produced grasslands and also oak and/or pine-dominated savannas and woodlands. Savannas and woodlands have a tree overstory and an herbaceous ground layer because fire controlled tree regeneration. Frequent fire, therefore, was effective at removing fuel accumulation in the form of trees. Historical accounts, which range in time from earliest Euro-American settlement to the early 1900s, and in space from the east coast to the west coast, consistently state that in the absence of surface fire, rapid tree growth occurs. Prescribed burns were known to prevent high-severity crown fires that occurred, like in the Great Lakes states. However, fires were considered wasteful to forest products, not just in tree damage, but loss to understocked forests. At this point, year 2021, the experiment seems to have demonstrated that fire exclusion is more costly than loss of forest products. Here are some of the catastrophic fires that prescribed fires were understood to prevent and probably at the same time scared people into the modern day era of fire suppression. There are severe fires that are ecologically appropriate, however, with severe fires occurring about every century. Surface fire exclusion involves active fire suppression combined with lack of deliberate ignitions, that is, the cultural shift. Land use that prevents fire spread due to limited or no vegetation is a powerful surface fire excluder. With fire exclusion is the transition from open forests of savannas and woodlands to closed forests, where tree fields accumulate, resulting in less frequent but more severe fires. So we asked, what about current effectiveness of field treatments at landscape scales by interviewing case studies. After large wildfires, fire managers often document how field treatments contribute to influencing fire behavior and severity through direct observations during a fire event. The data are qualitative, consisting of lessons learned, tools, barriers, and other components that may inform managers about implementation and longevity efforts associated with these large landscape field treatments. The challenge of case studies is that each one is unique, but when combined, these papers provide general outcomes specific to landscape field treatment planning, implementation, and effectiveness. In collaboration with the USDA National Forest Service Library personnel, we searched multiple databases. We located over 2,000 publications, which we filtered to 16 case study papers that met 3 criteria. Manager evaluation of the effectiveness of a field treatment for specific wildfire events at landscape scales. 8 of the case studies were identified from the formal literature search process, and we used back citations to locate another 8 case studies. This symposium includes presentations about the empirical and simulation papers, and the next presentation will synthesize overall results. 15 of the 16 case studies were relatively well distributed across ecosystems of the western United States. Types of treatments including thinning, prescribed fire, previous wildfires, timber stand improvement, commercial timber harvest, plantations, and mastication. In these images, you can see the treatment by removal of trees that were surface and ladder fuels which increase flame lengths and fire severity. Here's an image that contrasts how high flame lengths were in an untreated area with smaller ladder trees compared to how short flame lengths were in a treated area without those ladder trees. Here are images of fuel accumulation at the stand and landscape scales. In an image of an untreated stand that was burned with many saplings that provided ladder fuels for crown fire, and an image of extensive crown fire behavior in an untreated landscape. I like this image of a mixed severity burn and that the canopy fuels were far apart, but there was a dense accumulation of smaller trees. We then posed a series of research questions to extract information from each study and synthesize results of the combined case studies. Our objective was to examine the ways by which a fire event combined with the presence of fuel treatments affected management decisions and subsequent post-fire outcomes, in addition to identifying lessons learned through experiences. Questions to be answered by the case studies included: how did landscape fuel treatments mitigate adverse effects of wildfire? Did the fuel treatments influence fire suppression strategies and firefighter safety? Are there barriers to the development, implementation, and maintenance of fuel treatments that may have influenced the fuel treatment effectiveness? Are there identified research needs to focus on minimizing these barriers or enhance the effectiveness of fuel treatments at the landscape scale? Managers define fuel treatment effectiveness at landscape scales primarily as a decrease in fire severity. For example, the flame length reduction from crown fires to surface fires within treated areas compared to untreated areas. Treatments generally worked as intended, diminishing fire severity from crown to surface fires, limiting torching and spotting, and reducing heat intensity and effects in terms of large diameter tree mortality and loss of structures. Treatment effectiveness was often limited during periods of extreme fire weather. Although fuel treatments were not designed to stop fire spread, newly treated or burned stands did stop some fires, and slower rates of spread were more common in treated stands. Fuel treatments presented suppression opportunities that otherwise may not have been available, enhancing suppression resources and allowing better control. Treated areas along roadsides particularly reduced the time needed to prepare for burn operations. Also, reduced fire severity contributed to firefighter safety, or at least perception of safety. Treatments resulted in better positioning to use wildfire to treat fuels and maintain ecosystems, lengthening fuel treatment effectiveness. Larger treatments were more effective than smaller treatments, which were easily overwhelmed by large fire. The treatment of placement adjacent to previous treatments and wildfires, land uses that reduce vegetation, or natural fire breaks of non-flammable features such as wetlands or rock outcrops will amplify effectiveness. Alignment with prevailing winds places treatments in the path of where fires are most likely to occur, and orienting treatments to maximize the distance a fire travels through the treated landscape can increase the effectiveness of the treatment on fire progression. Treatments on flat topography and along ridge tops were more effective in reducing fire severity than treatments on steep slopes. Steep slopes exhibited higher fire intensity, and thus mid-slope locations were often considered most at risk. Ridges were often the best place to treat fuels because fire usually slows down while cresting and before heading down the other side. Although these case studies cumulatively advance understanding of landscape treatment effectiveness, critical research needs remain about treatment effectiveness at landscape scales. Science gaps involve spatial data about treatment area relationships with fire, costs and benefits of different fuel treatments, longevity of treatment effectiveness to develop maintenance schedules, and interaction of treatments with topography and prevailing winds to increase treatment effectiveness. At stand scales, we wondered if fuel treatment types that removed large diameter trees and supported release of small diameter tree growth were very temporary measures that in time created exactly the conditions that lead to high severity fires. We learned from synthesizing manager experiences that planning and deploying a treatment design that integrates terrain, prevailing winds, fire or treatment history, and infrastructure will be more effective than a design that does not. Large treatments were better than numerous small treatments. Actionable information for managers about treatment design at landscape scales to increase effectiveness primarily included leveraging treatment placement through adjacency to prior treatments or fires and alignment with the prevailing winds and topographic fire breaks. Prioritization of placement in relation to suppression needs to protect infrastructure is critical, and likewise, treatment placement can take advantage of adjacency to land uses such as roads and fields that act as fire breaks. Thank you for listening.
Thank you, Brice. I'm just seeing if there's any questions concerning Brice's talk right now. So, Brice, you've listened to both Shawn and you've listened to Jeff and you've listened to Sharon. One of the things that I find challenging in our synthesis is that they're almost independent pieces of work. The case studies are independent from the simulation, from the empirical. How do we start merging this really diverse set of information into one story? Do you have any ideas based on what you learned from these case studies?
Isn't that your job? I mean, it seems like they're pretty complementary, don't you think? That in some cases they support each other, in some cases they support each other by providing different lines of evidence. So I actually think they fit pretty well together, or they appear to be fitting pretty well together. You know, Shawn said we can see that the treatments are effective, but we don't know how they're effective or what makes them effective. And I think these manager observations help to maybe provide some observations of what seems to be effective.
There was a question by Matt that Shawn answered and Jeff answered, and I was just wondering if Sharon would have any way to chime in. Because we have a few minutes, it's only 13 after, we have till 11:20 to start the last session. So one of the questions that Matt asked is, given the federal agencies situation, and we're going to be getting an influx of money, if there isn't sufficient evidence to optimize treatments, how would you suggest we move forward? And Shawn did a really good answer to this question. He basically says, that's a good question and a big question. And Shawn did not have a good answer for many of the reasons pointed out in the presentation. There's going to be extreme variety and project level objectives. So to a certain extent, that will drive many decisions. For example, protecting wildlife and structures in the wilderness will be different than protecting projects further afield. But to move our knowledge forward so that implementation achieves goals of mitigating fire effects at broad spatial levels and untreated areas, some of these funds could be applied to designing experiments that once and if a fire moves through, the data obtained could inform what works better. The amount of time it could take to learn from this approach could be long. So sustained commitment and patience would be necessary. But this problem is no different than any other difficult problem we address with science. It has to be done in a structured way so that we can obtain the data that allows the level of inference we desire. I think it's a good point that Shawn makes. And one of the things that I thought from Brice's work as far as the manager's input, I think there are some different issues that the managers are dealing with that may inform some of the empirical research as well as the model simulations. As Sharon said, there is the social and environmental elements that we need to measure to determine whether it's good, bad, or indifferent. And I think that from that perspective, Brice, are there some key points that you would think would be the most critical things that a manager could bring to the table as far as what are those social and environmental aspects that you might have gained in the case study synthesis?
Well, I mean, the key point is we're trying to protect infrastructure and humans, right? So adjacency and prioritization of treatments near, where there are human densities and infrastructure would be critical. The managers also pointed out that if you can magnify your landscape, your treatments by putting it next to something that's already pretty, that acts as a fuel break, that works well. And a lot of human infrastructure does act as a fuel break. So they're already set up to align that way.
Okay. Thank you. Does any of the other panel members, Sharon, Shawn, or Jeff, we have about 4 minutes if you want to answer any of those questions.
Yeah. Can you hear me, Terry?
Yes, I can.
Yeah. So, yeah, I agree with what Brice and Shawn, Jeff said. I really think it's as far as moving forward to respond to Matt's question, it seems like there's not a one size fits all. It's going to be a lot of modeling approaches, and then based on managers' experiences, and then as different field treatments get actually challenged by fire, using that for the empirical data. So I think we have to use all the approaches available to us and take the long view, like Shawn said, that it's hard we can put out these very large, install these very large fuel treatments in a experimental way, but if they're not ever challenged by fire, or if it's 5 years later or 10 years later or 1 year later, all that, and depending on the when those fires burn, it's very hard empirically to to design a replicated study to test that. And so that's why I think we have to start aggregating these responses up in some sort of consistent manner over larger spatial scales, and then use modeling to try to inform future how we respond, how we change our treatments in the future.
Shawn, do you have a comment?
No, I think those are great. When Sharon was speaking, the one thing that popped in my mind for the first time ever, there's a webinar last week, I think, that's all running together, but it showed that the number of fires increasing tremendously in northern Washington state. So I was wondering if people have predictions of where the likelihood is greatest for fires in the coming year, because Sharon brings up an excellent point. Not only do we have to wait for a fire, but if the further time goes along, it kind of dilutes the power of the experiment, so to speak. So if you could have a high likelihood of where wildland fire will occur, focus your treatments there. But there's really, at least for my pea brain, there's no way of getting around the process of science. And, we still have thousands of people die every day of cancer. We have no solution to it. Science has been addressing that for my entire life. So some things take time, and this is one of them. Just the scale and the level of specificity of information we want, that level of detail of what works best, what shape, what density, how, where, why, are difficult questions when you really can't control the experiment, so to speak, whether or not a fire goes through, and then all the variables that affect the attributes of that fire.
Thank you, Shawn. I think we're going to move forward to our last talk, which is basically the one I'm giving. And it's really about tying all the pieces together. And so the last presentation is really going to be refocusing on the points that Joint Fire Sciences wanted to know. What is the state of understanding and key research in the landscape fuel treatment effectiveness? As I started, there were 5 main points. How are fuel treatments mitigating adverse wildfire effects? How are fuel treatments providing opportunities? what past and future wildfires are integrated into field treatment effectiveness, and can this literature synthesis inform future field treatment planning and identify management and policy relevant research grants. So this presentation is going to go through each one of these points, and I'm going to synthesize or bring the 3 stories or 4 stories together to see if we can kind of make some kind of synthesis or main points that we can address these questions. So the first one is, did fuel treatments mitigate adverse wildfire effects? This table shows the 3 different study types, and then the top columns are different wildfire effects. The in means inside the treatment, the out means outside the treatment. Dashes mean that we really didn't have any really good information or literature associated with that particular point of view. A yes means yes, they did mitigate adverse wildfire effects, and no, they did not. And so if you can tell from this table, we are identifying places that are weak in the case studies and empirical studies. And in general, the simulation studies are the ones that are probably providing the broadest breadth of information to address these specific things. The second thing I want you to know is that they're all yeses. And basically, we did find that fuel treatments do mitigate adverse wildfire effects. And in some cases, those can be outside the field treatment. For example, that of fire extent and the fire severity. Does fuel treatments provide opportunities? Once again, we look at all of these things, the same pattern for this table. And you'll notice that beneficial wildfire from the case studies didn't really say yes or no, but they really didn't quite answer how the beneficial wildfire could have been used. They did point out that treatments could be placed in next to other elements, such as beneficial wildfire. The empirical studies were probably the most complete as far as providing opportunities. And that makes sense because they're looking at a post-fire response and then evaluating them as to whether they turn around and had an effect on things like beneficial wildfire, fire suppression. A key point that was brought up across all 3 studies is that the effectiveness of any fuel treatment has to be placed within the context of topography and weather and wind direction. So we cannot separate fuel treatment effectiveness alone. It has to be placed within the context of the landscape. Long-term risk in itself, inside and outside, the simulations were the ones that actually addressed this the most as far as looking into the future. And that makes complete sense since both the empirical and case studies are a reflection of what happened, not what's supposed to happen. But I want to kind of focus a little bit more on those long-term risks. I think it's important to understand what long-term risk is. And Sharon did a very good job of introducing that, how we need to think about this from a variety of perspectives. The first thing that I think it's important is, what is the risk? In other words, what is the fuel stratum that we are dealing with? What is are we going to be focusing on surface fuels? Are we going to be focusing on ladder fuels? What is the longevity of how these vegetation grow and die and the dynamics over time? I think that's really critical if we're going to look at long term. So we got to think about those hazard states, how they relate to fuel conditions, and how they may influence fire behavior over time. The second thing is we need to add those risk states. And they considered hazardous for a particular outcome or a fire occurrence. In other words, risk states may be something that might be different in a WUI than, say, at a much more larger landscape resilience. And both of them have value. So many times we've been looking at fuel treatments for the more populated areas, but as Jeff mentioned, that, you know, if we look at the larger landscape, we can actually be more effective at altering landscape negative outcomes, considering landscape wildland fire. Maybe that's where we need to go with that larger focus, but then have some other different focuses that may be more closer to communities. And then consequently, I think one of the things that Sharon brought up was the consequence of an adverse event. in reality, she talked about the social aspects as well as the environmental aspects. And I think it's really worthwhile to glean what we learn from managers and the public and a variety of different collaborators to really understand what we're going to measure concerning that environmental component as well as that social aspect. So were past and future wildfires integrated into fuel treatment effectiveness? Yes and no. In other words, it makes sense from the empirical studies and the case studies because we are looking at how past wildfires may have influenced current or the current condition after this particular wildfire that was studied. They were very much a past. Only in the simulations did we actually look into the future wildfires that may exist. And this was actually probably one of the biggest things that I think that Shawn brought up, others brought up, that when is the next bad fire or hazardous fire that's going to occur? So did the synthesis inform future fuel treatment planning? Well, bottom line, fuel treatments work. That's not necessarily something we need to continue doing research. I think the challenge is how do fuel treatments work across the landscape? We need to really start changing the focus from the site to the landscape and to merge and dissect those, do a multi-scale situation from the site to the landscape, but we can't do it without the landscapes. We can't do it separate from them. One of the challenges we found in all the literature is what is a landscape? We know the ecological definition, but we really don't have a really solid fire definition of a landscape. If we're going to go and invest money on landscape, what is the size and severity of the fire event that's expected? What is the weather, topography, infrastructure interactions that are going to create that landscape? We need to be better at defining the landscape focus, and then how do we implement the treatments across that landscape? So maybe the thing that we need to think about is not only the social and the environment, but what is the landscape perspective on the social and what's the landscape perspective concerning the environment? Another thing is a new fire regime. So many times we think about doing fuel treatments within the past fire regime. We're going to control fuel treatments for a low intensity surface fire. In reality, the wildfires that we have today and in the future really need to think about what is the potentially worst fire regime. One often thing that the case study said is these treatments were not planned for the particular type of fire that hit them. In other words, fuel treatments really need to think about what is the type of fire that they are going to be created or designed to alter from a fire perspective, a fire behavior perspective. There was only a few studies in the case studies that actually ran the simulation models as they designed the treatments on the ground. So I think there needs to be a better, stronger link between that simulation and on the ground treatments in their deployment. Integrated management, one of the things that we need to think about is how to focus on disturbance resilience and integrate the management objectives with fuel treatments. We need to think innovatively. In other words, there's wildlife habitat, but how do we integrate fuels management in everything that we do? It isn't one size fits all. It's really much more of an integrated approach. We need to think innovatively. We cannot burn enough acres using prescribed fire. So how can we use wildfire in a much more effective way? Longevity is going to vary over time and space. So long-term reduction of risk is really going to vary, and we need to consider that. And we need to articulate the desired post-fire outcome under what fire behavior that we are expecting. I think it's really important to consider those things. What are some management and policy relevant issues? I think the case studies were the most broad in providing this. One of the challenges we have is we can do the science, we can do the modeling, we can do all that stuff, but it does not do anything until we get it on the ground. So we have challenges, competing resource objectives and values of risk. We have limited and declining funds and people to make it hard to implement. We need to increase our communication and planning with collaborators and agency partners. We need to be able to train them and show them what are the trade-offs that occur with this. We need to extend our what's the trade-off between extensive low-cost treatments versus intensive high-cost treatments. We have uncertainty on where the next damaging wildfire will occur. So even though we may have great ideas of doing much more broader empirical studies, we really don't know where the wildfire will occur. So it's kind of this catch-22. And are fuel treatments keeping fires small? In other words, are fire ignitions within fuel treatments being suppressed and not being allowed to be used to their most effective use of allowing them to burn? And one of the things that we don't know is how effective the treatments are at keeping fires small. So that's one area that we thought was really important for the scientific community to pursue. And one of our biggest challenges, treatments are not finished before the wildfire occurs. I manage 3 experimental forests, I do research on them, and any project I have will take anywhere between 3 to 10 years to completely implement. So consequently, we're actually always behind, and we need to speed up our ability to implement treatments. The thing that I think was really interesting, and me being a silviculturist, a lot of the treatments were described as mechanical, commercial, non-commercial, prescribed fire, and thinning. And I think it's more important to really focus on the particular fuel strata that's being actually changed or shifted. So a prescribed fire really influences ground fuels and surface fuels. A commercial thin is always going to be focusing on the crown fuels because they have to be large enough trees to actually make a commercial amount of money. Non-commercial or pre-commercial are always focused literally on surface fuels and ladder fuels. Mastication tends to be more surface fuels and ladder fuels. And then thinning. A lot of people use thinning as an economic, but there are very many different kinds, and there's some literature that already focuses on what kind of thinning, what crown fuels are being treated. Are there some ladder fuels that are being treated that are of economic value? I think that the research needs to really focus on a crosswalk to these particular fuel strata, because otherwise we as managers, it's going to make it much harder to put it on the ground if we don't know what fuel strata is being focused, and how are we going to be able to communicate to collaborators and people on the ground if we can't really describe what we are actually treating. Identify management gaps, expand to other ecosystems. Most of the research was done in the West in forested ecosystems on ponderosa pine and Douglas fir. We had limited research in the range, woodland, savanna ecosystems, and definitely not on the southeastern or northeastern United States. I think there needs to be research focused on these other areas because they're just as valuable for wildlife and other purposes. There is a limitation on cost-benefit analysis. We really don't know the cost-benefit between intensity or extensive field treatments. We need to integrate vegetation dynamics if we're really going to look at long-term risk. We need to know that surface fuels is the most rapidly changing strata, followed by ladder fuels, and then crown fuels are probably the most longest lasting, depending on the productivity of the site. Simulation, we need to integrate suppression opportunities into our simulation models. We should always include an untreated control. I think Jeff really showed how fuel treatment effectiveness as a function of a control really does indicate whether we're being successful or not. We need to include burned area as a metric, and we need to highlight interactions with combinations. As Jeff said, these were the most valuable studies where we treated a factorial experimental design in the simulation models. So I close with that. And I often tell managers when we're talking about fuel treatments and we're talking about what we need to do, if there was a wildfire in your area, I think this is the bottom and the most important question that you would ask somebody, a homeowner, someone who really loves the place where they live. Would you be content with the result? I think that's really the bottom line. And with that, we are at 11:35. We have 5 minutes left for our last, to close off this particular special session. So do we have any questions? Okay, I think I would like to open it up to our panel to add any comments or thoughts. based on what we just finished talking about, and also based on what I presented. Are some things that I may not have included that might be important to consider in our, as we tie everything together.
Nice job, Terry. I thought you did a great job.
Teresa, it looks like I've got a direct
Well, Terry-
message question. Do you like me to read it for everyone?
Brice has something to say. Please have her present, and then I can address the question.
Absolutely.
I'm sorry. Terry, I was interested when you talked about the small fires. It actually sounded like you would like to see those small fires spread. Is that what you were, and did I mishear you? Is that what you intended to say?
I'm not sure, but I think one of the things that's happening is that there may be a lot of fires being suppressed in the field treatments, and we don't know how many of those are being suppressed. So we may only have, so what we're really being tested in these field treatments are the big fires that take off. And so what are the effectiveness of field treatments at keeping fires small? And I think that was what I meant. I don't know if I said it clearly.
That's what I thought we were saying, but then it sounded like you were interested in actually letting some of those fires, like maybe letting some of those small fires go. So I was interested in that perspective. So anyway, I'm sorry.
No, I think that's an important point. And Sharon brought that up, I believe, in our document that we're preparing, is that we should allow fire to function in those treated areas as they were intended to. And there's opportunities, but to be totally honest, I think there's a lot of fear in letting that go, resulting in an adverse effect. We do have a question from Ed Brunson. He asks us, will we be expanding on the research gaps in the report for the Joint Fire Sciences? And yes, Ed, we will be expanding those reports. It's kind of hard to do it in our 15-minute slots, but you kind of basically saw the topics of each of the areas that we'd be expanding on the research gaps. Any other comments from any of the people that presented today? We have 2 more minutes. Okay, with that, I think we are done for our session. Thank you everyone for joining us, and have a wonderful conference.
Thank you, Terry. I just want to thank you to all of the speakers for sharing your expertise with us today. This session will be available in Whova, the conference app, within 2 weeks after the Congress has ended. We're going to take a 20-minute break now before beginning our next set of breakout sessions at 3 p.m. Eastern. There are 6 special sessions, each featuring a great lineup of multiple speakers and topics, as well as our first of the 2 virtual field trips. To choose the one you'd like to join, use the agenda tab to the left of your screen and click sessions. You can also click sub-sessions for more details about what to expect. To join the session offering Spanish and Portuguese interpretation, be sure to select the session titled Wildfire Simulation under Future Climate Change, Methods and Applications. Thanks again to our speakers and enjoy the rest of your day.